Today we're going to talk about series and parallel circuits, which are just two ways of combining up resistors together. So the basic rules of a circuit are that for all places in a circuit diagram, the current in has to equal the current out. And you can kind of see why that needs to be the case in the picture at the right. If you had more current coming into a place than going out, you'd be getting like a backup of charge. And if you had more current coming out of a place than going in, then it wouldn't really make sense. Where would it be coming from? The second rule is that if you go across a resistor, you must experience a potential difference that follows Ohm's law, V equals IR. And the last rule is that when you complete a circle, when you get back to the same place that you started from, you must end with the same potential that you started with. If we think of potential as being like a height on a hill that sort of determines how much energy you have, this makes sense because every time you walk on a trail, maybe you walk up a little bit on a mountain, you walk up a little bit, down a little bit. If you walk around in a circle and get back to where you started, you should end at the same height that you started at. So those are your three rules. So the goal is I want to be able to put multiple resistors together in a circuit, and I want to know what that does to the resistance. What I would really like would be a law that looks like Ohm's law, V equals IR. The problem is V equals IR only works for a single resistor, so we going to try some math, see if we can get a solution here. So the first kind of circuit I'm going to talk about here is series circuits. And a series circuit is just defined by a circuit where charge has to go through every individual resistor one at a time. So think about like the World Series, a series of events, or a movie series, or a TV series. You have to do everything one after another. So series circuit is the same idea. So the first question I asked you to consider was how the current through these different resistors would compare to each other. So you've got a 9-volt battery, you've got 3 resistors here connected up in series. So the question is, how does the current through resistor 1 compare to the current through resistor 2 compared to current 3? And the answer is, well, if current in has to equal current out at every spot, including this place and this place here, then I think it becomes pretty obvious to you that all these currents have to be the same. How do you think the voltages are going to relate to each other and to the 9 volts? So again, that should be relatively obvious from rule number 3. So if I start here and I'm at, say, 0 volts, the low side of the battery, if I cross the battery, now I'm up here, I'm at 9 volts. And then I cross resistor 1, I experience a potential difference of V1. So I drop by an amount V1. If I cross resistor 2, I drop by some amount V2. And if I cross resistor 3, I drop by some amount V3. And then I'm back to where I started. So I think it should be pretty obvious that the 9 volts here, which I'm just going to call V total here, has to equal V1 plus V2 plus V3. So now let's put all this stuff together. I could use Ohm's law for each individual resistor. So V1 is just going to be I1R1. So the current through resistor 1 times its resistance. V2 is going to be I2 times R2, so its current times its resistance. And V3 is going to be, yep, that's right, I3 times R3, its current times its resistance. But remember, all these I's are the same I, so I can just pull the I out, and I can get R1 plus R2 plus R3. And on the left-hand side, I've still just got the total voltage, V. So this looks like V equals IR. Remember, my goal was to write a V equals IR for the whole circuit that I could use in the whole circuit. The V equals IR rule that I had before was true only for individual resistors. So that means I can locate over here. I can identify that this right here is the R. And I'm going to call it R total or R equivalent. So that means that for a series circuit, if I want the resistance of a bunch of resistors put together in series, I can just add the resistances together. So what would the resistance be of these 3 resistors together in this circuit shown? Be 3 kilo ohms plus 10 kilo ohms plus 5 kilo ohms, so it would be 18 kilo ohms, exactly. And then just a note to make that when you put 2 resistors together in series, the resistance becomes larger because you get less current for the same amount of voltage. So a parallel circuit means that the charge has a choice of which resistor it wants to go through. So think about parallel lines or two lines that don't meet. Think about parallel universes, which is you think about as like two universes that are happening kind of side by side and don't like run into each other. So that's the idea of parallel. If you've got multiple things happening in parallel, another example is parallel processor computing. So take a look at the circuit here. I've got a 12-volt battery, and I've got my charges coming out of the positive terminal. I'm going to call this the total current, I total. And then what happens is I've got these different branches. So I guess we're going to call this branch I2, just based on how they've labeled it here. I'm going to call this branch I3, and this branch is going to be I4. So those are the three branches that the current could go through. So think about how the voltages have to compare to each other. So I hope it makes sense to you that since everything touching the positive side of the battery terminal is at positive 12 volts, I hope it's not too controversial that I am basically arguing that all of this stuff here that's directly touching the positive battery terminal is at 12 volts, positive 12 volts. Similarly, everything on the other side that's touching the negative side of the battery terminal, which I guess we'll do in blue here, all of this stuff is going to be at 0 volts. Right, we got a 12 volt difference, so if it's 0 volts on the negative side, then it's 12 volts on the positive side. So that means that every one of these individual resistors has got a potential difference of actually all 12 volts across it. So V1 is actually equal to V2, is equal to V3, which is actually equal to the total voltage, or the voltage of the battery. Now the piece that ties this all together is, how do the currents relate? How does I1, I guess they're calling it I total, I1, how does I total relate to I2, I3, and I4? Well, take a look at one of these branching points right here. I hope I can convince you that basically, because the current in equals current out, that the total current has to equal I1 plus I2 plus I3. The currents have to add together. You can see that either on one side or the other. And if you don't believe me, you can kind of smear all these points right here together to like a single branching point for everybody. It's kind of a little misleading in this diagram. Again, we can use Ohm's law for the individual resistors, so we know that V equals IR. So I guess that means that I is equal to V over R. So I get I total is going to be V total over R total, which we don't know yet. We don't know what the total resistance is. I1 is going to be V1 over R1, and then plus I2, which is V2 over R2, and I3 is going to be V3 over R3. But wait, are the V's any different, or are they all the same? We already said all the V's are the same, so V total is the same as V1, is the same as V2, so I don't even need to call them V1, V2, V3, or V total. I can just call them all V. If they're all V, then they all cancel, because I can divide both sides by that same V. And you wind up with your rule for how resistances work in parallel, which hopefully I can draw legibly here. You get that 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So give that a try on the circuit on the left and tell me what you think the total resistance should be. So this would be 1 over 2 ohms, 1 over 3 ohms, 1 over 4 ohms. So what we've got to do in the example given here, we've got to find a common denominator. So it looks like our common denominator here is going to be 12, I guess? 12, yeah. So this is 6/12 plus 4/12 plus 3/12. 6/12 plus 4/12 plus 3/12. 6 plus 4 is 10, plus 3, you get 13. So this looks like 13/12. 13 over 12 ohms. And you might think you're done, but you're not. This is 1 over the answer. So you have to remember to flip it one last time. This is what students always forget to do. So you get that our total is actually the reciprocal of that, the flip of that. So our total is actually going to be 12 over 13, 12/13ths of an ohm. And then just to note that you get a smaller resistance when you add multiple resistors together in parallel, because you get more current for the same amount of voltage, because now you have more paths for the current to travel through.